So today I'm going to talk about Electron and Electron security. My name is Luca. I do OPSEC since 2004, worked in a different company, a bunch of roles. Most recently, I co-founded DoinSec. We're a security consulting boutique with office in San Francisco and Warsaw, Poland. You're here for Electron. I assume you know what is Electron. I'm going to give you a quick overview, give an overview of what's the ecosystem. We'll be talking about security model, which is, of course, very important, and then go deep into weaknesses in terms of design and implementation bugs that we found. The talk is mainly focused on framework-level vulnerabilities that apply to basically all Electron apps. And there is a small part at the end of the presentation when I'm going to give more advices that are towards security issue in application with the checklist and the tool. If you want to make comments, questions, you want to do follow-up, you do extra research. There was no much, of a public research on Electron, so I kind of expect, you guys to go out there after and help, researching more on Electron. So if you want to use the hashtag electronegativity, that's an easy way to kind of follow the stream. Thanks a lot for, the experience I had with disclosing vulnerabilities. So thanks a lot to the Electron core teams and the GitHub security team. I think it was the best experience disclosing vulnerability in my entire career. And what happened was I sent, first batch of emails on, for a few of those issues. And I waited 24 hours, and then I got an invite on the private GitHub repo. And then a few minutes later, a private invite on a private Slack channel. And so my first reaction was, whoa, these guys are taking open source very seriously. It's like, go and fix it yourself. But then actually it was not the case. They really wanted to start a discussion around like, how do we fix these things? They shared a lot of the internal knowledge that they had, results from previous, security efforts. And, they kind of wanted me to work with them on thinking about what Electron 2.0 could be. And so it was really a very good experience, and I'm still working with them. And then a friend of mine, Claudio, for the help on the code that we'll be releasing. So what is Electron? It's a framework to build desktop app. And there is a big statement on the front page where it's, if you can build a website, then you can build a desktop app. And the idea is that if you know web technologies, then you can use the very same technology to build something that run on a desktop. When GitHub started Atom, the hackable editor, they needed a framework to base the editor on. And so they started thinking about leveraging, for example, Chrome embedded framework or Node WebKit to build this editor that could be modified easily by changing JavaScript and HTML. They realized they couldn't make and use those frameworks, so they decided, okay, let's build something that, let's implement something from scratch. And so Atom Shell started. It was open source in 2014, and then renamed in 2015 Electron. And it's currently maintained, and it has a very, very big community of companies and developers that are building apps on top of Electron. They have, 3 principles. It needs to be cross-platform. So when you build an Electron app, it has everything. The framework itself has everything you need to build something that would run on Windows, Linux, and OS X. So there are, of course, some API that are specific to an operating system. So there are APIs, for example, for the touch bar on OS X. But most of the other APIs are, cross-platform. It's modular. There is actually an idea that if you add a new feature to Electron, it must be a native API. Everything else should be an NPM modules. And then, as a developers, you shouldn't worry about how to build an installer, how to do software update, how to do debugging, desktop notification. Everything is within the framework, so you can leverage the tool of the framework itself. I guess you ask yourself, right, why are we talking about desktop app? I mean, it's 2017. Talking to a lot of friends that do web development, I kind of understand why it would make sense to build a desktop app. There are complex web applications where they're now compatible only for Chrome, which if you think about that, it doesn't make any sense, right? We thought about the web as an idea to build something that would be available on every platform and browser. But that's not the case. Moreover, there are situations where you want a bit more privileged access to the operating system. And for example, for performance, you may want to do some task on a client side. So if you have an app that needs to generate PDF, instead of having backend service that would do the rendering and creating PDF, what if you can move the logic to the client side? So it kind of makes sense. The two ingredients of Electron are libchromium content, which is a Chromium content module. So it's a library that basically include Blink and V8, which is the JavaScript engine. That's what Chromium and Chrome are based off. And then Node.js. And for me, it was very interesting when I kind of realized that the two main ingredients was libchromium content and Node.js, because I had extensive experience on Node.js, but I didn't know much about source code of Chromium. So for me, it was a good way to combine something I knew to something I was completely new to learn. And I can recommend you guys, like if you want to do a new research, that's a good way to approach. Like take something that you know and combine to something that you don't know, and that's the way to learn. If you look at an Electron app, the way it looks like is it's a bundle of libchromium content and Node.js as the main building blocks, and then you have Electron, the framework itself, a bunch of NPM, and then finally your code. And you're shipping all of these things, right? So you're shipping a bundle of these things. Electron app. So your code is inside an archive type of file, called app.sr. It's a new extension, a new format that is natively supported by Electron. What they did, they basically extended Node.js file primitives to transparently read files within the tar-like archive. So you can basically open this archive, and there would be a file called package.json, which includes metadata and everything you need to kind of define what's your app, what are the dependencies, what is the main process, and then finally you define, and you will start when you execute main.js, or you can rename those on any name, your main process. So there's a concept of main process and the render process. You always have one main process and multiple render process, as many as you want. And within the render process is where you would be including through a web view, something like HTML, CSS, and JavaScript. So we talked about main and render. Let me give you an overview of what is inside and what are the primitives that are available in those processes. So in main, you have what is called, you can invoke something called BrowserWindow, which is the way to basically create the tab equivalent in Electron, where it creates a web frame, and that's where you include the standard DOM. You also have access to some primitives that allow you to operate with the operating system, like showing an icon on the menu trail, or notification or things like that. You have access to Node.js primitives, and you have a mechanism that is based on IPC that allow you to communicate between main and render. So if we now look at the render, of course, you have the module to do the IPC communication, and we'll see in a second exactly how it works. You may or may not have access to Node.js API, and you have something called a WebView tag, which is a custom tag that's been included in Electron, where it will allow you to embed additional content. So how IPC work? It's kind of typical IPC mechanism. Where you have ability to send messages in synchronous way. So this is an example where the render is sending a synchronous message to the main with a ping, and the main would respond with a pong. And that's how your app can build some logic to communicate between render and the main process. But what is very interesting is that the same mechanism is also used for internal communication. So when you define an IPC call, you need to define the channel, right? And so internal Electron channels start with Electron _, and so those are internal messages. And there is no any filter on sending those messages from your app. This is actually an example on how the alert box is implemented. So the render would send this message to the main to pop an alert box. So quick kind of overview of the ecosystem. There are a lot of apps already built on Electron, from Slack to Visual Studio to WordPress to something like interesting, for example, WebTorrent. Many more apps. It's a very active and dynamic ecosystem. But NPM, it's one of the core components. So everything is a module. So you basically have access to kind of 500,000 packages of usable code. But as we all know, we had LeftPad that was unpublished and broke the internet. It was 8 lines of JavaScript, as far as I remember. And then most recently, there was a research on password reuse on how to obtain access to 40% of direct NPM packages, and I think it was like 52 or 54 in direct, NPM push permissions, which of course kind of shows that operational security, it's not always at the best. And well, if you use an NPM modules in your app, you need to be sure on from where it comes from. There are also NPM specific for Electron, particularly around tools. So if you want to have an app that at startup of the your operating system will start as well, then there's an NPM module for that. There are NPM modules for profiling. There are NPM modules for UI components and something like that. Okay, let's go to the security part. So I was thinking, okay, let's approach this security model thinking about a browser, and then I started Googling for what is the security model of the browser? I mean, I understand the security of the browser, but is there a formal definition? And so there's a great book, as you probably know, Threat Modeling, and then I found this quote, and I figured out it was the best one. It's complex to define the actual security model of the browser, but we all know that it kind of looks like that, right? You have a cat is visiting web pages, and then something happened. For Electron, there are some similarities, but also some differences. The similarities are, of course, untrusted content is something bad, but in Electron you have limited interaction. Forget about Brave, which is based on a fork of Electron. If you're not building a browser in Electron, if you're building like a normal app, generally you don't give ability to a user to go to a random URL, right? So there are some limitations on the way people interact with the WebView. On the other side, local resources are a kind of a new attack vector. So you can load, for example, malicious subtitles if you have a player app. On the isolation side, the things are not very good in a sense that in case of Electron, compared to a browser, you basically could have access to Node.js primitives. And the Electron, as you will see, supports limited Chrome-like sandbox. And so if you basically have an XSS, one way or another, you may actually get an RC. So whether the app doesn't use sandboxing at all, or you find a bypass, as I will show you in a second. But Electron is not a browser, and so that is very important to remember. There is a need to build something that is more open than a browser, right? Because we're trying to build desktop app. And so certain principles and security mechanisms are actually not enforced in Electron by design, and those are the problems that, some of the problems that you will see. But things will change in Electron too, hopefully. What are the, critical configuration of an Electron framework app? There is these things, and this is probably the most important one, called node integration or node integration in worker, which is a flag as part of web preferences that defines whether the render has access to Node.js, right? And this is implemented using Chrome isolated words, so that they have, basically it's a new V8 context, and that is available only read-only. To me, I mean, this is basically the difference between alert box calculator. So if you set node integration to false, well, you can't invoke Node.js API, so the best you get if you get an XSS is whatever you can do with an XSS. Otherwise, if it's true or you have a bypass, then you have very reliable RC bug. So if you do need to include untrusted content, you have two options. You can either use a browser window where you explicitly need to disable node integration, or you can use a WebView tag which has node integration disabled by default. So those are the two ways where you would basically include in your code, in your JavaScript to include untrusted resources. There is also another option, which is sandboxing. So while node integration governs the access or not to node primitives, it doesn't really protect you against what I call glorified Electron API. So we'll see in a second. Electron basically took some of the native JavaScript API and increased or improved the functionality. And if you just use another integration flag, you're not reverting back to the native JavaScript primitives. And so you need something else, which is sandbox. And you should think about sandbox flag as the native kind of a Chrome type of sandboxing. When you do have sandboxing, all the communication between IPC, all the communication between main process and render is through IPC. Of course, when you do sandboxing, Node.js integration is disabled. But there is a very important difference because with just Node integration, you still have Node.js code running inside. Like it just that the context you're removing references to Node.js primitives from global variables. Instead, with sandbox, it's equivalent to Chromium and Chrome type of sandboxing. So you have vanilla JavaScript rendering. How do you enable sandboxing? There is a flag, but unfortunately, in today's Electron, a flag alone is not enough. You do need to set a flag when you start Electron. Otherwise, not all browser window, not all WebView will have sandboxing. Actually, WebView is not even supported at this point, but not all basically web frame will support sandbox. So if you do want to have sandbox coverage across the entire app, you need to set up this command line argument. And unfortunately, you cannot even set up programmatically because by the time the JavaScript code in Electron is executed, it's too late to set up sandboxing on Chromium. So you do need the flag from the very beginning. Unfortunately, one of the one of the limitations of today's implementation of sandbox in Electron is that preload scripts, which are JavaScript, they are executed before the main process is executed, still have access to a few modules. So if you have untrusted code or a way to modify code in a preload script, and I found example in kind of real life apps, then you can use one of those two techniques to still get access to the full JavaScript modules of Node. So in the first case, you just use remote, which actually implements what you want, which is including Node.js primitives from the main. So you would basically get a reference of app as like the instance. Or the other one is to abuse what we just discussed about IPC. So you could make an IPC call using one of the internal Electron IPC mechanisms to get a reference of the app. So to avoid that, there's a new flag called context isolation, where basically it has separate context from preload script. So preload script can still access global variables, but they won't be able to modify. So things like overriding or monkey patching, which had a big role in previous vulnerability on Electron, they're not available here. 20-second digression on muon. So when I started reading about Electron, I was thinking, wow, okay, now I understand the framework. I can find a bug in Brave, which would be pretty cool, since it's a browser and you have way more ability to get people to visit the website. But Brave realized that Electron, as it is, right, it was not the best option as a framework to build a browser. And so they forked and improved their security. Particularly, they had modified the way the libchromium content source code is imported. So it's a kind of a drop-in replacement, so they can update the Chromium much faster. They completely removed Node.js from the render. They still use IPC, but it's a kind of a more controlled IPC mechanism. And they have Chromium's OS sandbox everywhere by default, which of course has a lot of advantages. So you can update quickly. All the same origin policy checks and any security features that you have in a browser, it's there. And even if you do find a bug, you still have sandboxing. So this is an open research. I asked the Bcrypt and the Muon community, do you guys have any idea what are the differences between Electron and Muon at this point? I think it would be pretty cool to see. And they replied with the GitHub issue. They asking for basically the same. So that's definitely an interesting and kind of a open research. All right, so let's talk about bugs. You look at an Electron app, and I try to summarize what I thought was a good way of distinguish between classes of bugs or classes of problematics. If we go from the bottom, you of course have libcommon content and Node.js, which are very critical. And if you do have vulnerabilities on those components, well, then that may affect your application. So if you have, for example, outdated vulnerable version, any bug on Chromium, libcommon content and Node.js would affect your application. Moreover, there are runtime flags. Disable web security, right, which will completely kill the same origin policy, would definitely affect your application. As you will see in a second, actually, disable web security, it's kind of pointless at this point because there are open same origin policy bypass, but hopefully in future, it would actually make a big difference. And then a level up, Electron itself has the problem again around outdated vulnerable version. So any framework level bug will affect all application, and your application if you're bundled, if it's bundled with the old version, a glorified API, and any custom flag. And then if you think about you as a software engineer building Electron apps, you still have all the classes of web security vulnerabilities on top of an insecure use of Electron API, on top of custom protocol handlers, and all different issues. There are a kind of a mix between web security and mobile security. So there is a lot of stuff if you want to build a good and a secure Electron app. And so my idea was, okay, can we try to focus on two areas which are the most interesting to me, which is framework level bugs and then application level bugs. I ended up with too much material, so today we're going to cover only Electron framework level bugs, and I think they are more interesting because of course they apply across all Electron apps. If you do enjoy this talk, please give a good positive feedback, so I will submit to Black Hat Europe and you guys can see the remaining part. Nevertheless, I decided, okay, let me see if I see like some mismatch on the foundation. And updating Chromium and Node, it's not an easy task. There are a lot of things that change in both projects. They're both very dynamic projects. And so the Electron dev community is very well aware. They established an upgrade policy, but it's kind of not guaranteed. So it is difficult. And it's particularly difficult if you think about backporting security patches, right? You need to keep track of what's changed, and you need to make sure that you are importing those changes. And so I spent a few nights looking at changelog of Node.js and libcromium content, and I got this pull request that was fixed in Node 7.6. And I couldn't figure out, like I couldn't find any reference, or I couldn't see in libcromium in Node.js used by Electron any equivalent patch. So if you do remember, Starcon and WuSign are two certification authorities that backdated certificates since there was the deprecation of SHA-1, and so they backdated a certificate. And of course, the CA community didn't particularly like this practice, and it got, they got distrusted by Chrome and Mozilla. And of course, other tools like Node.js had to start, removing those certs. But Electron was still on 7.4, and of course didn't have. So I notified the team, it got fixed. But this is an example where it is hard to keep track of all the changes. So of course, this one would allow someone with those certificates to do man in the middle on any Electron app. So framework level bugs are very interesting, and not just because they affect all platforms, but also because in this context, they could be either implementation bugs or deviation from what we would expect from a browser, right? Things around, is the same origin policy enforced? Is access to local file enforced? And things like that. Almost all of these bugs are, were discovered through source code review and documentation. Some of these issues are really like design level issues. So by just reading the documentation, you kind of feel like, oh, something is not right. Of all possible vulnerabilities, of course, node integration bypasses are golden tickets. And the reason for that is you find an XSS, and then you can use this XSS to and then you can use XSS to have some JavaScript, and then you can use your JavaScript, hopefully, if you have an exploit for node integration bypasses to access Node.js primitives, and then you suddenly have a very, very reliable RC. So I decided, okay, let's focus on node integration first, and let's see what's out there. And so I started reading, and I actually couldn't find much. There was a single blog post from 2016 where there was an overview of 2 bypasses. And as you can see here, they were very simple. This was a very early stage of Electron, where you basically could just insert, in the first case, in the window open, you could basically just insert the flag node integration true again. Window open was not considered as a new way to open new window. We talked about browser window and the WebView tag. Of course, there is window open as the kind of third option, so you could still pass an attribute. And the second one is around setting an attribute inside the WebView tag. So very simple issue. They were fixed, just after they were reported, and nothing else, right? So I couldn't believe that was the end of kind of node integration bypasses. So I decided, okay, I really want to know more about past vulnerabilities. And before starting to div stuff, I decided, okay, let me try to use reverse psychology. I'm sure now you will remember my logo. And so it was. My idea was, okay, do they have changelog? Likely from 132, there is a changelog where basically every change has an entry. And so I kind of challenge you now quickly to spot the security fix. Don't tell your neighbor, just think. So surprisingly, there was this sentence, did not behave as expected, in places where it really looked like security issues. And then I've noticed that there were a few cases where pull requests were actually not linked. So there was no link to the actual change, which sounded kind of like, strange. So I started diffing and, downloading all the changelog, grepping stuff, nothing really, super fancy. And basically, I obtained this list, which is almost the full list of vulnerabilities until 1.4. There is a big change in 1.6.8. So 1.6.8 is full of security fixes, but those are the one when I did the study. Electron core team is awesome. So I told them. So while discussing this issue, I told them how I actually studied the Node.js integration bypasses, and so they wanted to know exactly the process I had. And they understood why it's important to flag security issues as a security issue, because it could raise awareness, and people would actually update the framework in a quicker way if they know it's related to security. And they actually backport, they change basically all the changelog me to include security attributes, right? So you have the security tag on each security relevant fix, which is awesome because you can imagine is a lot of work. And so I really appreciate their help. So one of the example I kind of had to, I did to study the previous bypasses was, okay, let's reverse a backport. Of course, if you reverse a backport, it's easier because there is less, there's less code to check. And so in this example in 139, I noticed there was something related to node integration enable on the parent, but not on the child, and it had something to do with same origin. So after playing for a while, I kind of came up with this proof of concept where window opener eval, it's basically from the child is going back to the parent. At that point, you have node integration, so you can reach another window open, and at this point, you will have Node.js, right? But that was, again, was on 139, so we are on 1.6, and so was, for me, it was like, okay, let me see if I can actually figure out something on 1.6. So I started reading the documentation, and then kind of suddenly I realized that same origin policy, while it is enforces normal use cases, it is actually bypassable by design using one of the API, or by using simply like a window location type of trick, where you're just basically redirecting your page. So you could either load a page and then change the location, and of course point to JavaScript, or use window eval. And the way eval in Electron works, it is by basically you create a new window. What you get back is not a traditional instance of a window that you would get from native vanilla JavaScript engine, but it's an instance of browser proxy window. Browser window proxy, which is an Electron object that has extra methods, extra attributes. One of these methods, function, is eval, which allow you to execute code that is actually executed on the child, right? So you are getting a reference of a child, and then you can basically piggyback and execute code on the render. And so this is kind of a same origin policy bypass as a feature, which at this point is kind of complex to remove. There is a work in progress, and there are recommendations not to, for example, disable web security. But at this point, it's kind of irrelevant because, again, you can obtain same origin policy bypassing this way. So how can you leverage same origin policy to actually have emoticon execution? By looking at the code, I actually figured out a place where there was a privileged zone that was related to Chrome DevTools, where node integration was actually always enabled. And so you could basically build something like this, where you would point your window to the privileged location, and then get a reference of the child and eval, and at that point you would have access to Node.js primitives, and in this case, for example, just using exec file to write a file. So this was reported on May 10th. It was fixed on a few days later. Interestingly, the Electron core team was actually already working on a fix, and it was, I think, released 2 days later. They have a good mechanism of notifying maintainers of app, like primarily like big apps. So I think it was quickly fixed in kind of all major Electron apps. There is a long tail of apps, so I wouldn't be surprised if there are other apps out there that they are still on previous version. If you do need to update, update to 1.6.11, that has also the fix for the man-in-the-middle certificate stuff. All right, so let's see if the 2 demos work. All right, so what we have here is simply an Electron app that is bringing, actually, let me show you. It's a simple Electron app that is opening a browser window, and as you can see here, node integration is set to false, and it's opening on attacker.com. We can see here that, for example, process versions. There is no reference of process, so that shows that there is no access to Node.js primitives here. So this example is the simple same origin policy bypass. So we're using eval to basically piggyback and send JavaScript code. So nothing very exciting. We are opening a page that, as you see here, it's hosted on attacker.com, but then we're actually injecting JavaScript to pop an alert box on example.com. More interesting is the SOP2RC. So the way it's actually implemented this exploit is with the example I gave you before, but Node.js execution is actually made in a, I think, more interesting way, where instead of leveraging pure Node primitives, you could leverage Electron primitives, particularly around open external, which is a primitives to open external apps, to run arbitrary commands. So you're basically using Electron primitives to kind of compromise Electron itself, which of course is kind of interesting. So This is, of course, very reliable. There's nothing, well, demo should work on this case. All right, let's go back. So we talked about glorified API, and the example I gave you around the browser window proxy is a very good example of what is a glorified API. But there are, of course, more and more examples. And the idea is that if you do enable sandbox, you need to revert back to a vanilla JavaScript engine, right? So you shouldn't have access to any glorified API if you are in a sandbox environment. And so there is a case where, particularly around HTML5, where that was not true. There are a few more examples. This is just one of them. So what is HTML file path? So if HTML5 included new primitives to to deal with files. So for example, if you do an upload of a file using HTML5 primitives on Internet Explorer, in order to protect the path, the browser will use a fake path, right? It will literally have fake path, and then the file name would actually be the original file name. This is meant to, first of all, protect file system path, but also, usernames, right? Because the user name could be part of the path if you're accessing file on the user directory. Electron increased the functionality of HTML5 by including an attribute called path that would actually return the real path on the file system. And unfortunately, this is not reverted back, even if sandbox is true. And so, basically, a remote web page or could leverage this bug to basically leak the full path and the username if it's inside a user directory. This was reported on May 10th. It is kind of complex, and again, sandbox is still a experimental feature, so it's still open. And unfortunately, I have the feeling that there are many issues around glorified API because it really requires reverting back to vanilla JavaScript for all these APIs. Let me do a time check. All right, I guess we can. Well, it's not very exciting, but let me do it anyway. So we can enable sandboxing. So this should be back to standard lib Chromium content, so we can try to upload a file. And as you can see here, you still see the full path. And again, there are a few more examples on these APIs, but and again, it's a difficult problem to solve. Sandbox, by the way, it's not even enforced right now in WebView. So, like if you're building an Electron app, you still want to enable sandboxing, and you need to load untrusted content. You still want to use sandbox, but again, with the limitation that you have in today's. All right. All right, and let's talk about deviation from browser standards. So we talked already about same origin policy enforcement, lack of enforcement. It is a difficult problem to solve, and this will probably be one of the main issues that will be fixed in version 2.0. There are fewer restrictions around privacy and secure user experience. We'll see an example, and then access to file handler. So for privacy and security relevant features, think about HTML5 media capture API, which is an API that allows you to capture and record video and audio stream. We all know that if you visit a web page that wants to leverage this API on a regular browser, you get a pop-up saying a remote origin want to access your camera. But we're dealing with desktop app, and the Electron app does not display notification, so which means that if you have an XSS, you basically have a mechanism to do and capture screenshot video and audio recording. And again, those are not the things that are easy to fix, because if you're building a desktop app, you certainly don't want notification all the places, right? So, I mean, it is tricky to build something that is a desktop app and do leverage, you know, web resources and web technology. Access to file. So today you can open a file handler on Electron. It's an open issue, so that means that any web page can you know, read local resources, and this could even be done without you know, user interaction. So if you have an Electron app and it's loading, or you can inject some JavaScript, like it's loading untrusted resources, or it's or you can inject you know, an XSS, or you know, run random HTML. Well, then you can read local file. So this is an example. There are other techniques. This, I think, is an interesting technique because it would work even, you know, when same origin policy enforcement and other would be a bit more, you know, better implemented, better design. And it's based on loading a remote, an attacker control Samba share to then load a file which contains an iframe that will load the actual local files. And so with that, let's try this one. Let me actually see. Firewall off, because we like to be with our firewall. So if this thing works, so it's mounting the share. Of course, you know, you could probably have overlay, or you could open a new window to hide the progression bar. But I mean, this demo, I kind of want to show you what's going on here. Let's see if it actually works. All right, so it mounted the remote one, and then if the timing is right on the other calls, it should actually open the file, and this is basically the content of etc passwd. And I mean, the fact that, you know, file handler are supported, that's the problem, and then also the fact that same origin policy is not enforced, it doesn't makes things better. So any basically old school trick on browser, but you can think in this context as well. So let's talk now about apps, right? Because so far I just discussed around framework level bugs. There is definitely more than that. So you can think about traditional web security vulnerability, an insecure use of Electron APIs, and all this mismatch between Electron and the browser. We did do the study around this. There is no time to show you today. We are releasing today a white paper. It's 25 pages of kind of developer-friendly guideline on how to build secure application. It can also be used by, you know, pen tester and auditors, but it's mainly towards, you know, building secure apps. So those are 13 steps and 13 things you want to have and check if you're building an Electron apps. And with that, we are also raising a tool called electronegativity that is basically facilitating the check of those issues, right, on those configuration. Electronegativity is nothing else than an ST parsing using a Sprima to basically explore JavaScript and look for the issue discussed in the checklist. Everything will be available on our site, and the tool will also be available on GitHub. All right, 5 minutes. Okay, perfect. So conclusions. So it was an interesting research personally. Again, I recommend if you want to do a new research, combine something you know with something that's difficult and you don't know, and so that's the way to learn. It was a very nice experience to look at browser code. You get to learn a lot of other things. And thanks to, you know, the research we did, you know, there's been several improvements on Electron. Some of them, they are actually not on this presentation. They will be as part of version 2.0, which is going to be kind of the security game changer, where there's going to be an easy mechanism if you want to import untrusted resources, whether they are local or remote. Kind of the approach of, you know, security by default. With today Electron, you don't have security by default. It is still possible to build secure apps, but you kind of need to know the nitty-gritty details so that you can use either custom flags or application code to figure out a way to mitigate framework-level weaknesses. So an example of that is you can, for example, have a callback. So there is the ability to have a callback that every time someone clicks on a link, you can inspect the destination of the link. So what I've seen implemented in several apps, they are probably very well aware of the fact that you can import local files. What they do is they do a callback, a check. They check what's the destination. If it's a file handler, then they would basically block the call. But of course, then you have problem around 302 redirect, whether it's done through an actual 302 redirect or a meta tag refresh. So things get complicated, but I mean, if you do know web security, you can build an Electron app that is secure today. It is just more kind of a complex. Future work, and that's future work for me and for you guys if you want to go and explore. Electron versus Muon, it's very interesting. If you do find a bug in Muon, you have a bug on Brave. They also have a bug bounty, and I think it's a good idea of of a browser. So that's kind of interesting work. Now that there is electronegativity, I'm thinking to kind of understand what's the state of Electron app security. I've done kind of a check on on different apps, but I don't have a good understanding of all the Electron apps that are listed in the official repo or on the official web page. Would be interesting to see, for example, how many of them use node integration false, how many of them use sandbox, which by the way I suspect is almost zero, which you have custom protocol handlers and things like that. So it wouldn't be too difficult to build statistics and do a survey. And then finally, of course, more vulnerability research on the framework itself. That's the hand. We still have 2 minutes, so I guess a perfect time for question and answer. Luca Carettoni on Twitter. That's my email. Add the electronegativity hashtag, and more than happy to follow up on any question. Thank you.